Right, so the last section in number theory we look at is congruences. Now you need to have a very good understanding of divisibility in order to understand congruences. So hopefully everybody's on the same page. Right, so let M be a positive integer. We will say that the integer or the numbers or integers A and B are congruent modulo M, right? That's the definition we use. So they're congruent modulo M, and we denote that by A is this means congruent. So A is congruent to B modulo M, or mod M for short, if A and B give the same remainder when you divide them by M, meaning that if I divide A by M, obviously you're gonna get a remainder. The remainder could be 0, but you get a remainder. And you do the same thing here. With B, you're gonna get a remainder. So we say that they're both congruent if the remainder is the same, basically. So if that doesn't happen, then we say A is not congruent to B, mod M. Examples. Right, I'll talk about these lemmas after. So for example, 5 and 2. If you divide 5 by 3, right, you're gonna get 1 remainder 2. We don't care about the number, you get the 1, right? We just care about the remainder. So you divide 5 by 3 and the remainder is 2, right? And obviously 2 is the same as 2. So 2 is congruent to 2 mod 3, that's true. What about here? If I divide 23 by 6, right, I'll get 6 3s are 18, remainder 5. So I get, 23 is basically congruent to 5. What about minus 1? Now with the minus, basically you could think of this as minus 1 divided by 6 is basically 1 remainder 5. You could think of it that way. Is that correct? That doesn't seem correct. Right, I'm trying to think of a nice way to convert this from a negative number to a positive one. Right, basically you could just think of it as adding, so you could add a multiple of 6 to this and you'll get minus 1 plus 6 is 5. So minus 1 is congruent to 5, right? When you have a congruence, you can just add multiples of this number to it and it'll still work. But basically if you think about it, minus 1 and 5, the difference between those is 6, right? So it's a multiple of the number, so it works. 25 is not congruent to 2 mod 4 because 25 is actually congruent to 1 mod 4. If you divide 25 by 4, you get 6 remainder 1, so the remainder is 1, which is not 2. All right, A is congruent to B mod 2 if and only if A are both either even or odd. That one is straightforward, right? Because mod 2 is easy. That's usually we don't consider easy things like that, but sometimes it helps. All right, now coming back to these lemmas. So we say A is congruent to B mod M if and only if M divides the difference. So you could, how congruences work, right? They work very similar to equations. So you could think of, if this was an equal sign, right? Then I would have A minus B is equal to 0 if I carry the B on the side. And that part of it works the same with congruences. So if I had A is congruent to B, it means that A minus B is congruent to 0 mod M. And now remember we're saying that two numbers are congruent if they leave the same remainder. But on this side I will have 0, so the remainder is 0. Right? So basically what I'm saying is that A minus B, when I divide that by M, the remainder is 0, which means that M is a divisor of A minus B. That's how I get this. Another way you could do it, which is the most logical way I think in terms of understanding it, is, and this is actually sometimes used as a definition rather than how it's defined here. So A is congruent to B mod M if and only if A is equal to B plus a multiple of M, right? For some integer multiple K, right? So basically if it's congruent, it means that there's an integer multiple of M I can add it to B to get A. Either add or subtract, right? Because it's an arbitrary, well, It's a constant K using any multiple. Right, so again, if A is congruent to B mod M, that's the same as saying A is equal to B plus some multiple Km. So when you're proving things with congruences, this is usually the way to do it if it's like a basic proof, like one of these things on here for theorem 50. Right, theorem 50 gives some statements that are true for congruences. These, when you're working with congruences, these are important to know. So I'll go through these in detail, at least in some detail. The first one is straightforward, right? Like I said, congruences work similar to equations. So if A is congruent to B, it's the same as saying B is congruent to A, once it's the same modulo, same mod M. All right, if A is congruent to B mod M, right, then the GCD of A and M is the same as the GCD of B and M. And how you would do this is use this lemma 48 up here. So A is congruent to B mod M means that A is equal to B plus Km, right? So if you take the GCD of A and M, it's the same as the GCD of B plus Km and M. And then you can subtract the Km and you'll get the GCD of B and M. So using the divisibility or GCD properties from before, you could show this. If A is congruent to B mod M and B is congruent to C mod M, then so the first is congruent to the second and that second is congruent to a third, it means that the first is congruent to the third. So this is like the transitivity property for divisibility. Right, so the first one will be congruent to the third one mod M. Right, if you have a congruence, A is, so now we're going to look at things we could, ways we could modify congruences. So if A is congruent to B mod M, I can add any number to both sides of that congruence. So if I add C to this side, I can add C to this side, and it still works, right? For any integer C. Now I can also multiply, right? If A is congruent to B mod M, I can multiply both sides of that by C, and it's the same thing. It's congruent. AC is congruent to BC mod M for any integer C, Z, C and Z. Right. Now, in addition to just multiplying, there's a difference between the fifth one and the sixth one here, right? In the fifth one, I just took any integer C and I multiplied both sides of the congruence, but I didn't affect the modulo. I didn't do anything with M. Now, I could actually take C and multiply it by the entire thing. So I could say, well, E is congruent to B mod M, AC is congruent to BC mod MC. Assuming that C is positive, right? Because modulo is defined for positive things in here. This one you don't really use as much though. This is the one that's most useful. So if the seventh one, if A is congruent to B and C is congruent to D, now I'm gonna stop saying mod M every time, right? Because you know what it is. So I'm just gonna say if A is congruent to B, C is congruent to D, then I can add or subtract both of these like an equation. So I could take A plus C is congruent to B plus D, or I could take A minus C is congruent to B minus D, and it's still valid. And again, same thing, I can also multiply across. So I can take A and multiply by C and B and multiply by D, and it's still valid. What I could also do is take A is congruent to B and raise both sides to the same power. So if A is congruent to B, then A to the power of N is congruent to B to the power of N for any positive integer N. All right, so I could square both sides, or I could cube both sides, and it still works. All right, now this one says if A is congruent to B mod M and A is congruent to B mod N, then A is congruent to B mod the product. If C is a positive integer, now, okay, so this one here is basically the converse of this one here, right? 6. So what you have is that this thing is an if and only if statement essentially. So if C is a positive integer and AC is congruent to BC mod CM, then you could just divide throughout by C. But note here, you have to divide everywhere by C. You can't just divide in here and then forget about this one. Right? The one that lets you divide in here and forget about this one is only this property. This is the cancellation property, and this is important to note, the distinction between this one and this one. So in order to cancel this C without affecting this, you need the GCD of M and C to be 1, meaning that you can only cancel a number in a congruence if the number is relatively prime to the modulo. So, what do I have here? Right, so GCD of M and C is 1 and AC is equal to BC mod M. All right. I can only cancel this C here if C doesn't have any common factors with M. Right, and then I get A is congruent to B mod M. If I did not know that C was relatively prime with M, then I can't do this, because it's possible that M has a common factor with C, and then you can't do this one. You have to do something similar to this, where you would have to actually go and divide by the modulo by whatever the common factor is. The last one here, I kind of forgot to mention, well, it wasn't stated, but I took it off from the divisibility part of it. This also works for, you could think of it as divisibility, in the divisibility sense as well. If A is congruent to B mod M and f of x is a polynomial, you could call it P of x if you want, with integer coefficients, that's important, then f of A is congruent to f of B mod M. Now, another way of saying this, right, is if M divides A minus B, then M divides f of A minus f of B. And that's what was originally stated in the divisibility part, but I actually took that off. Right, so again, if A minus B is a multiple of M, then f of A minus f of B is also a multiple of M. And again, this is only for polynomials, right? So I use f, but I probably should have used P just to make sure you know it's a polynomial, not an arbitrary function. If you see a polynomial with integer coefficients, then this thing might be useful. All right, does anybody have any questions with congruences so far? Because that was just the basic stuff. There aren't any examples, so let's just look at a couple of these. So determine whether or not 10 and 99 are congruent modulo 7. Well, the answer to that is obviously no, because the remainder here is 3. The remainder here is 1, I think. Yeah, so they're not congruent. Find the remainder when 8 to the power 2020 is divisible by 7. Right, so one thing to note is that 8 is congruent to 1 mod 7, right? So if 8 is congruent to 1 mod 7, then 8 to the power 2020 is congruent to 1 to the power 2020. Right, using this property here, 9. And 1 to the power 2020 is just 1. So it means that this thing is congruent to 1 mod 7, which means that when you divide this by 7, the remainder is going to be 1. This one is a similar idea, but you have to be a little more creative with it. So 8 would be congruent to 3. Now, 3 alone doesn't help you because it isn't 3 to the power 2020 is still some work to do. But you could consider that 8 squared would be congruent to 3 squared. Right? And 3 squared is 9, which is minus 1 mod 5. Right? In this case, it's easier to use the negative numbers because the negative number is smaller than the positive. Right? I could say 9 is congruent to 4 mod 5, right? And that would be true, but then I would still have a fairly big number to work with. Plus and minus one are usually easier to work with. So 8 to the power of 2 is basically 3 to the power of 2, which is minus 1. It means that 8 to the power of 4 would be plus 1, right? Because if you square minus 1, you get plus 1. So if 8 to the power 4 is 1, then I just need to raise both sides of that by 505, I think. And because 505 by 4 will give you 2020. Right? So basically, the answer in the end will again be 1. Because 1 to the power 505 is 1. So this thing is congruent to 1 mod 5. This, you all can try to do divisibility test for 3 and 9, right? So how do you prove that? And you could, well, you do it using congruences, but you can go through that. Okay, the next thing here is quadratic residues. All right, now you can also have higher powers, so you can have cubic residues and those things, but we'll just kind of focus on quadratics. So for any given positive integer m, the quadratic residues mod m are all positive or all possible integers in the range 0 to m minus 1, right? Such that x squared is congruent to that number. So what we're looking for basically is all possible numbers from 0 to m minus 1, where you can square a number and then get that square some number and get a number in that range. So if I consider m is 3, right, mod 3, right? If I square, usually how you do this, if you want to check, you would list the numbers. So you start with x's, you can use 0 if you want, but you'll always get 0. So start with 1, 2, 3, 4, 5, 6, 7. So you draw a table. I don't have it prepared beforehand, so I can't show it to you. But when you're checking for quadratic and cubic residues, you have a table. The first column will be x, right? All the possible. So you have start with say x is 1, 2, 3, 4, 5, 6, 7, and you keep going as far as you need to go. The second column will be x squared, and then you can look at say, well, okay, what's the remainder when you divide x squared by whatever the mod is. So if x is 1, right, then x squared is 1, so the remainder is 1. If x is 2, x squared is 4, right, and 4, the remainder is again 1. If x is 3, 3 3s are 9, the remainder will be 0. So what you'll notice for quadratic residues is that there is always a pattern that repeats. So it'll go from 0 to whatever this is minus 1, and then it'll repeat. Sometimes it may repeat before that. So what will happen is, as x goes 1, 2, 3, 4, 5, 6, it'll repeat 1, 1, 0, 1, 1, 0, 1, 1, 0. There's a pattern. Meaning that if you square any number, you can only get congruent to 0 or 1 mod 3. It's impossible to get a square being congruent to 2 mod 3. Right? That's important to note. This here is actually very useful when you're trying to prove things have no solutions. Right? So, well, before I'll show you this just now. So if you get an equation, right, and the equation basically has something like a squared is, I don't know, 2 is 3x plus 2, then that thing doesn't have any solution, because that would mean that a squared would have to be congruent to 2 mod 3. There's an example before that uses mod 4 I'll show you. Similarly for mod 4, so again, you list x is 1, 2, 3, 4, 5, 6, etc. You square it and look at the remainder. So 1 squared gives you 1 remainder. 2 squared is 4, that gives you 0. 3 squared is 9, that gives you remainder 1. And then it keeps going. So 0, 1, well, starts with 1. So you get, the table will look like 1, 0, 1, 0, 1, 0. You only get 1s and 0s. You will never get a 2 or a 3. Right? So basically, again, if you're solving an equation and you see a perfect square has to be congruent to 2 or 3 mod 4, automatically, no solution. So you can look at this equation here. Right? I have x squared plus y squared is equal to 2019. Right? Note that if you consider mod 4, this thing here is congruent to 3 mod 4. So is it possible to add 2 perfect squares and get a number that's congruent to 3 mod 4? And the answer is no. Right? Because x squared could only be congruent to 0 or 1. Y squared, again, could only be congruent to 0 or 1. They don't have to be equal, but the possible values here are 0 and 1. and here is 0 and 1. So if you consider all possible cases, you can either get 0 plus 0, 0 plus 1, 1 plus 0, or 1 plus 1. Meaning that this sum could only be 0, 1, or 2 mod 3, mod 4. Right? 0, 1, or 2 mod 4. But this number is 3 mod 4. So this could never be equal. There are no integer solutions to this thing. And that's why you could use mods or congruences to help you identify where there's no solution. Right? You could even go further for any other prime. So x squared could only be congruent to 0, 1, or 4 mod 5. It could never be congruent to 2 or 3. Right? X squared, again, if you consider mod 7, it could only be 0, 1, 2, or 4. It cannot be 3, 5, or 6. Right? And as I said, you could make similar observations for cubic residues. Cubic residues for these smaller numbers don't necessarily give you much. Like for cubic residues, you'll get that x cubed has to be 0, 1, or 2, which doesn't help. Because 0, 1, or 2 mod 3 is all possible values. Right? Usually the quadratic ones help you a lot more. Right, this part isn't so much fundamental. So I was considering whether to skip this, but it's not long, so I'll just go through it. So if A and M are relatively prime, then there exists a unique integer A star such that A times A star is congruent to 1 mod M. Right? Where A star lies between 0, strictly between 0 and M. It can't be 0 and it can't be M. This A star is referred to as the inverse of A modulo M. So it's like an inverse, right? Because you multiply A by A star and you get 1. So that's, in that sense, we think of it as an inverse. So the modular inverse is 7 mod 23 is 10, because if you take 7 and you multiply by 10, you'll get 70, which is the same as 1 mod 23. So this here is a star if A is 7. Sorry, this here, 10 is a star if A is 7. Similarly, if you consider mod 48, 7 is a self-inverse. 7 times 7 is 49, which is 1. Mod 40. Now, when some useful things to note when you're working with inverses, anytime you get a number like this that's bigger than the modulo, just reduce it to something smaller, because it's usually easier to work with. And that could easily be done by subtraction, or sometimes you might have to add to bring it up. All right, note here, if AB is congruent to 1 mod M, then A and B must both be relatively prime to M. Because if they had any common factors with M, this would be impossible. You'll get, this thing here would have to be, it wouldn't make any sense. Because this would mean that M divides AB minus 1, but there's a common factor with this and this, so that common factor should also divide this. All right, what we're going to look at now is congruences of this form. So if I want to solve this, so basically I have numbers A, B, and M, and I want to find the value of X satisfying that. This is what theorem 61 tells you, when there's a solution or where there's no solution. So let A, B, and M be integers where M is positive and C is the GCD of A and M. So if the GCD of A and M divides B, right? Again, this is the equation you have to look at. So we're looking for the GCD of A and M. If that GCD does not divide B, which is what I had just mentioned, then this thing has no solutions, right? Because it divides this and it divides this, but it is divided. Remember this thing, you could rewrite this as AX is equal to B plus a multiple of M. So if you take the multiple of M on the left-hand side, you'll get AX plus, minus the multiple of M as B, right? If C divides if C divides A and it divides the multiple of M, it divides the left-hand side, but it doesn't divide the right-hand side, so that's a contradiction, right? If C divides B, all right, so these first two cases are assuming that C is greater than 1 to start with. So if C divides B, then this thing has exactly C incongruent solutions mod M. What this basically means is that if you consider the solutions mod M, they're exactly C of those. Now, in practice, though, you wouldn't write it like this, and I'll show you what I mean by that in the example later on. This is just something you could check to see that you've actually solved it properly. Right? If C is equal to 1, there's a unique solution modulo M of this thing. So there are 3 examples here. And I'll explain how you actually go about solving these. So first of all, consider this congruence. 7x is congruent to 1 mod 48. Right? How you solve something like this, first thing you should check, what's the GCD of 7 and 48? The GCD of 7 and 48 is 1. Right? So once the GCD is 1, you're okay. There will always be a solution. Right, now what you're going to do is, if I go back up to this thing here, when you're solving these congruences, this one here is very important, right? Property 5. And which other one? Mainly property 5, and then the other one is really just using the definition of what it is. Right? So what we're doing is we're going to multiply by things. Now, be careful when you're doing this. We're trying to solve for x. When you're trying to solve for something, you should never multiply this congruence by anything that has a common factor with the modulo. Right? So if it's mod 48, you should never multiply by anything that has a common factor with 48. Meaning the number can't be even, it can't be a multiple of 3. So the idea here is to multiply this thing by something that will make the coefficient of x a nicer number than 7. Right? And when I say nicer, I mean something smaller. But you're really going to have to increase it before you could decrease it. So what I mean is you're going to have to multiply the entire equation by a number and get some multiple of 48 basically plus something. It's kind of difficult how I'm trying to explain it verbally here, but if you consider this equation and this congruence and you multiply it, the entire thing by 7, what happens? You're going to get 7 sevens, 49x is congruent to 7. Right? Mod 48. So 49x is congruent to 7 mod 48. Now that 49x is really 48x plus x. Right? And as long as you have a multiple of 48 or a multiple of this, you could just ignore that in the congruence. Or you could think of it as subtracting it. Right? Subtracting or eliminating or whatever. Because remember, you're looking for the remainder. So if I divide 48x by 48, I'm going to get 0. Right? So you multiply this by 7, you get 49x is congruent to 7. And then you just subtract 48x, so you'll get x is congruent to 7. Right? That's where you get the solution. All right, I just want to make sure you all understand this. So what I want you to do is tell me what is the solution to, let's say something simple. 5x is congruent to 2 mod 7. All right, so I hope you all have some pen and paper there. Write down 5x is congruent to 2 mod 7 and tell me how you would solve that. All right, after we finish this part, we'll pause and then restart because the stuff that comes after this is a little more advanced. All right, so anybody has any ideas?
Multiply by 3.
Okay, so if you multiply 5x is congruent to 2, if you multiply both sides by 3, you'll get 15x is congruent to 6 mod 7. And then you subtract 14x and you get x is congruent to 6. Yep, that's good, that works. Another way you could have done this actually, there are many different ways you could do it, right? It's just up to you to come up with one way that works. An easier way that could work is if you consider 5 and 7, those are very close together, right? So instead of multiplying, what if I subtract 7x from this? 5x minus 7x will give you minus 2x is congruent to 2 mod 7, right? Now, both numbers, they are even. 7 doesn't divide, 2 doesn't divide 7, so I could actually cancel that 2. And I'll get minus x is congruent to 1 mod 7, which is the same as x is congruent to minus 1. And minus 1 is the same as 6 mod 7. So the same answer in the end.
Could we have said
Yeah.
5x is congruent to 2? That means that 5x is also congruent to minus 5 mod 7.
Yeah,
And then
same
divide by
idea.
5.
That works as well. It's the same idea. And then cancel. It works. That is correct. Also, what I want to mention here that I didn't really mention before is what this idea of congruence is. So let's work with the same 5x is congruent to 2 mod 7. So I know that x is congruent to 6 mod 7. So I can actually list out the values that work. I know minus 1 works, 6 works, and I could just keep adding 7 and all those numbers will work. So 13, 20, 27, all those numbers are solutions to that congruence. Meaning, for example, if I take x is 6, right? 6 times 5 is 30. If I divide 30 by 7, I'll get remainder 2, 28 plus 2, so remainder 2. If I take x is 20, all right, that was another one. 20 times 5 is 100. The highest multiple of 7 less than 100 is 98, so again, remainder 2. So all of these numbers work. The way that when I say x is congruent to this thing, basically, this is just a shorthand way of saying, well, every number that is of the form 7 plus 48k will work. This is just a simpler way of writing it. Similarly, when I say x is congruent to 6 mod 7, I mean x is really 6 plus any multiple of 7. And any multiple I choose will give me an answer. Now, one thing I want to mention here. So if I take this, x is congruent to 7 mod 48. Actually, no, I'll mention that when I get to example 64 because it's more applicable there. All right, I'll finish this and I'll give you all some to work on your own, and then when we pause. So this example 63, congruence 6x is congruent to 1 mod 48. Now notice 6 and 48, did you see that those is 6, right? 6 doesn't divide 1. This has no solution, and you can actually check it manually if you want. What about this one? 6x is congruent to 12 mod 48, right? Again, did you see that these two is 6, right? 6 divides that, so what I could do is I could divide everything by 6, right? That is this one up here. So if I have a common factor with everything, I divide that throughout. It's property 11. So if I divide throughout, I'll get x is congruent to 2 mod 8 because I'm dividing throughout by 6. In this case, I've actually already gotten what I wanted. Sometimes you have to do more work. Now this here is automatically the solution. I can stop with that. This part where I talk about here is just mentioning what I mean by the C incongruent solutions. So in this case, C is 6, right? C is the GCD. GCD is 6. So based on what this theorem says, I should get 6 different solutions. Right? Here I only have 1, but this 1 is congruent mod 8. This says I should have 6 solutions congruent mod M, which is 48. How you would obtain those 6 solutions is start to list them. So if x is 2, right? 2 mod 8 is the same as 2 mod 48. If you think about it, right? Because if it's 2 mod 8, it's actually the other way around. 2 mod 48 is the same as 2 mod 8. Right? Because if you divide by 48 and you get 2, then if you divide by 8, you'll also get 2. Right? But these also work, right? Because if I divide by 48 and I get 10, then if I divide by 8, I'll also get 10. But I can divide that further and get 2. And same thing for all of these numbers. If you divide all of these by 8, the remainder will be 2. So when I talk about having 6 incongruent solutions, mod 48, these are the 6 solutions 2, 10, 18, 26, 34, 42, mod 48, right? But practically, it doesn't make sense to write it in this form because that's a lot more work. It makes more sense to leave it like this. It's only if you wanted to check that you did it correctly, then you would list it like this and say, okay, I have 6 of them. The GC was 6, then that's okay. Although in practice, you're not really going to do that. All right, write these down. I want you all to work on them. So I want you to solve 13x is congruent to 4 mod 23. All right, I'm not going to bother with the one with no solution because you all know how to check for that. Let's say 12x is congruent to 4 mod 22. It's a nice one, I think. And 17x is congruent to 5 mod, let's say 37. So take about 5 minutes and try to solve those and tell me what the answer is. So I'll pause your recording here and then restart when we rejoin. So actually take 10 minutes because I'm gonna go take a break and walk outside.